The Sun, a colossal sphere of hot plasma, is the heart of our solar system, a source of life-sustaining energy that influences every aspect of Earth's existence. This immense star, located about 93 million miles away from Earth, emits energy that travels across the vacuum of space and impacts our planet in ways fundamental to life as we know it. Without the Sun, Earth would be a frozen, lifeless world, devoid of the warmth and energy essential for sustaining life. Solar energy, primarily in the form of electromagnetic radiation, is the driving force behind Earth's climate and weather systems. The Sun emits energy across the electromagnetic spectrum, including visible light, ultraviolet, UV, light, and infrared radiation. When this energy reaches Earth, it warms the planet's surface, influencing atmospheric and oceanic circulation patterns. The differential heating of Earth's surface plays a crucial role in creating weather systems. The equatorial regions receive more direct sunlight year-round compared to the polar regions, resulting in warmer temperatures at the equator and cooler temperatures at the poles. This temperature gradient drives atmospheric circulation, leading to the formation of wind patterns that transport heat and moisture around the globe. These circulation patterns are responsible for various weather phenomena, from gentle breezes to powerful storms. For instance, the trade winds and westerlies are large-scale wind patterns driven by solar heating. The Sun's energy also contributes to the formation of high and low pressure systems, which affect precipitation and weather patterns. Photosynthesis is one of the most significant processes that depend on solar energy. Plants, algae, and certain bacteria capture sunlight and convert it into chemical energy through a process that involves chlorophyll. During photosynthesis, carbon dioxide and water are transformed into glucose, a form of sugar, and oxygen. This process not only produces the oxygen we breathe but also forms the basis of the food chain. Plants and algae are primary producers, meaning they create their own food and, by extension, provide energy for herbivores. Herbivores, in turn, serve as a food source for carnivores. Thus, solar energy indirectly supports all forms of life on Earth by initiating the flow of energy through ecosystems. The relationship between photosynthesis and solar energy is so fundamental that it affects the global carbon cycle and climate regulation. Forests, grasslands, and oceans act as carbon sinks, absorbing and storing carbon dioxide, which helps to mitigate climate change. The productivity of these ecosystems is directly influenced by the amount of solar energy they receive. Humanity has harnessed solar energy for thousands of years, from ancient sun-baked mud bricks to modern solar panels. In recent decades, advancements in technology have enabled us to convert solar energy into usable forms more efficiently. Photovoltaic (PV) cells, which are made from semiconductor materials, absorb sunlight and convert it directly into electricity through the photovoltaic effect. Solar panels have become a crucial component of the global energy landscape, offering a renewable alternative to fossil fuels. By capturing sunlight and converting it into electrical power, solar panels reduce reliance on non-renewable energy sources and help to decrease greenhouse gas emissions. Solar power has the potential to provide a significant portion of the world's energy needs, contributing to a more sustainable and environmentally friendly future. Additionally, solar thermal energy systems capture the sun's heat to produce steam, which can drive turbines and generate electricity. These systems are used in various applications, including solar power plants, solar water heaters, and even solar cookers. By utilizing the sun's energy for heating and power generation, we reduce the environmental impact of traditional energy sources. The sun is a central figure in the story of life on Earth. Its energy drives climate and weather systems, supports photosynthesis, and has been harnessed for human use through technological advancements. Without the sun, life as we know it would be impossible. Its influence is a reminder of the intricate connections between natural processes and the vital role of solar energy in sustaining life on our planet. As we continue to explore and utilize solar energy, understanding the sun's role in sustaining life helps us appreciate its significance and the need to protect this precious resource. The sun's radiation is not merely a source of light and warmth but also a potential threat to life on Earth. The sun emits a broad spectrum of electromagnetic radiation, including visible light, ultraviolet, UV rays, and X-rays. While visible light is essential for life and photosynthesis, UV and X-ray radiation can be harmful to living organisms. Fortunately, Earth's atmosphere plays a crucial role in shielding life from these more dangerous forms of solar radiation. The ozone layer, a region of the stratosphere approximately 10 to 30 miles above the Earth's surface, is essential for protecting life from harmful UV radiation. Ozone, O, molecules in this layer absorb the majority of the sun's harmful UVB and UVC rays. Without the ozone layer, increased levels of UV radiation would lead to severe health issues, including higher rates of skin cancer, cataracts, and other UV-induced diseases. The ozone layer also protects various ecosystems, including marine and terrestrial life, by preventing UV rays from disrupting biological processes. In recent decades, human activities have led to the depletion of the ozone layer due to the release of ozone-depleting substances like chlorofluorocarbons, CFCs. This depletion has resulted in increased UV radiation reaching Earth's surface, causing environmental and health concerns. International agreements like the Montreal Protocol have been instrumental in reducing the use of these harmful substances and aiding in the recovery of the ozone layer. Earth's magnetic field, generated by the movement of molten iron in the outer core, extends into space and forms a protective shield against solar wind, a continuous stream of charged particles emitted by the sun. The magnetic field deflects most of these charged particles away from the planet, preventing them from stripping away the atmosphere and disrupting electronic systems. The magnetic field creates two regions of charged particles known as the Van Allen belts. These belts, located above Earth's atmosphere, trap and hold charged particles from the solar wind. They act as a barrier, protecting Earth's surface from high-energy cosmic rays and solar particles. This protection is crucial for maintaining the stability of our atmosphere and ensuring the safety of satellites and other space-based technologies. Auroras, or the northern and southern lights, are visible manifestations of the interaction between solar wind and Earth's magnetic field. When charged particles from the sun collide with gases in the upper atmosphere, they produce glowing displays of light. These spectacular light shows not only provide a visual feast but also serve as indicators of the dynamic interactions between solar wind and the magnetic field. Solar flares and coronal mass ejections, CMEs, are intense bursts of radiation and streams of charged particles released during periods of heightened solar activity. These events can affect space weather and have implications for Earth's magnetic field and atmosphere. While the magnetic field protects us from most of these impacts, strong solar storms can induce geomagnetic storms, which may disrupt satellite operations, communication systems, and power grids. Understanding and predicting space weather is crucial for mitigating the effects of solar storms on modern technology. Space agencies and observatories continuously monitor solar activity and provide forecasts to help prepare for potential disruptions. By studying solar phenomena and their interactions with Earth's magnetic field, scientists can better predict and manage the impacts of space weather on infrastructure and technology. The sun's role in providing energy and light is balanced by its potential to pose cosmic threats. Earth's atmosphere and magnetic field work in tandem to protect life from harmful solar radiation and charged particles. The ozone layer absorbs dangerous UV rays, while the magnetic field deflects solar wind and traps high-energy particles. Understanding these protective mechanisms highlights the delicate balance required to sustain life on Earth and underscores the importance of ongoing research and international cooperation to safeguard our planet from cosmic threats. The sun's energy is not constant. It varies over an approximately 11-year solar cycle, during which the number of sunspots and solar activity fluctuates. These variations influence Earth's climate in several ways. During periods of high solar activity, known as solar maximum, the sun emits more radiation and solar wind, which can lead to minor increases in global temperatures. Conversely, during periods of low solar activity, or solar minimum, the sun's radiation decreases slightly, contributing to cooler global temperatures. Sunspots are cooler, darker areas on the sun's surface caused by intense magnetic activity. Their number and distribution follow an 11-year cycle, with peaks and troughs corresponding to solar maximum and minimum phases. The variability in sunspot activity affects the sun's total energy output, albeit in subtle ways. Although the impact of sunspots on global temperatures is relatively minor compared to other factors, they are still a key indicator of solar activity and can provide insights into long-term climate patterns. The sun's differential heating of Earth's surface creates temperature gradients that drive atmospheric circulation. Warm air at the equator rises and moves toward the poles, while cooler air from the poles sinks and moves toward the equator. This circulation pattern creates various climate zones and influences weather systems, such as trade winds, westerlies, and polar easterlies. The sun's energy also affects precipitation patterns and storm formation. Increased solar radiation can lead to higher evaporation rates, which contribute to cloud formation and precipitation. The energy from the sun drives the hydrological cycle, in which water evaporates from oceans, lakes, and rivers, forms clouds, and eventually falls back to the surface as rain, snow, or other forms of precipitation. Changes in solar radiation can thus influence the intensity and distribution of rainfall, impacting agriculture, water resources, and weather patterns. Solar activity can influence the El Niño and La Niña phenomena, which are major drivers of climate variability. El Niño is characterized by warmer than average sea surface temperatures in the central and eastern tropical Pacific Ocean, while La Niña is characterized by cooler than average temperatures. Both phenomena impact global weather patterns, including altered precipitation and temperature extremes. Changes in solar radiation can contribute to the intensity and frequency of these events, although other factors also play significant roles. Over geological timescales, variations in solar output have contributed to significant climate changes. For example, the Earth's orbit and tilt relative to the Sun change over long periods, affecting the distribution of solar energy and contributing to ice ages and interglacial periods. These variations, known as Milankovitch cycles, interact with solar radiation changes to influence Earth's climate on timescales of tens of thousands to hundreds of thousands of years. The Sun's influence on climate and weather has historically affected human societies. Periods of low solar activity, such as the Little Ice Age in the 17th century, coincided with cooler global temperatures and had significant impacts on agriculture, economies, and societies. Conversely, periods of higher solar activity, such as the medieval warm period, were associated with warmer temperatures and sometimes more favorable growing conditions. Understanding the Sun's influence on climate is an ongoing area of research. Scientists use climate models to simulate the effects of solar variability on global temperatures and weather patterns. These models incorporate data on solar radiation, sunspots, and other factors to predict future climate scenarios. Advances in solar physics and climate science will continue to improve our understanding of the Sun's role in Earth's climate system and help inform strategies for addressing climate change. The Sun's influence on weather patterns and climate regulation is a complex and dynamic process. Through solar cycles, radiation, and atmospheric interactions, the Sun plays a crucial role in shaping Earth's climate and weather systems. Understanding these processes is essential for predicting climate variability and preparing for future changes. As we continue to study the Sun's impact on our planet, we gain valuable insights into the intricate connections between solar activity, climate, and human societies. The Sun's energy extends beyond its role in climate regulation. It also influences geological processes on Earth. Solar energy contributes to the movement of the Earth's lithosphere, the rigid outer layer of the planet that includes the crust and the upper mantle. The differential heating of Earth's surface plays a role in driving plate tectonics, which is the movement of the Earth's lithospheric plates. The Sun's energy affects the Earth's surface temperature, which in turn influences the thermal convection currents in the mantle. These convection currents are responsible for the movement of tectonic plates. As solar energy warms the surface, it causes the mantle to heat up and become less dense. This thermal gradient generates convection currents that drive the movement of tectonic plates, leading to phenomena such as earthquakes, volcanic eruptions, and mountain formation. The Sun's energy is also integral to weathering and erosion processes, which shape Earth's landscapes. Solar radiation drives the weathering of rocks through both physical and chemical processes. For instance, the heating and cooling of rock surfaces cause thermal expansion and contraction, leading to physical weathering. Solar energy also drives chemical weathering by facilitating reactions between minerals and atmospheric gases, such as oxygen and carbon dioxide. Solar energy is a key driver of the hydrological cycle, which involves the movement of water through the atmosphere, surface, and subsurface. As the Sun heats the Earth's surface, it causes water to evaporate from oceans, lakes, and rivers. This evaporated water forms clouds, which eventually release precipitation. Rainwater and snowmelt contribute to erosion by carrying sediments and shaping landscapes through processes such as river carving and sediment deposition. Soil formation is another geological process influenced by solar energy. The combination of weathering, erosion, and biological activity, driven by solar radiation, contributes to soil development. Solar energy supports the growth of vegetation, which, through processes like root growth and organic matter decomposition, contributes to soil formation. The interaction of weathered rocks, organic matter, and climate conditions results in the development of diverse soil types. The formation of mineral deposits is influenced by geological processes driven by solar energy. For example, the movement of tectonic plates, which is partially driven by thermal convection currents influenced by solar heating, contributes to the formation of mineral deposits such as ores and fossil fuels. The interaction of geothermal energy with solar-driven processes also affects the formation and distribution of mineral resources. Solar energy indirectly impacts the availability and distribution of natural resources. Fossil fuels, such as coal, oil, and natural gas, formed from ancient biological matter that was originally supported by solar energy through photosynthesis. The energy stored in these resources was captured over millions of years as plants and algae converted solar energy into chemical energy. Understanding the role of solar energy in the formation of these resources highlights the interconnectedness of Earth's systems. Over geological timescales, variations in solar output have influenced Earth's climate and geological processes. For example, changes in solar radiation can affect the intensity of ice ages and interglacial periods. The interactions between solar energy, climate, and geological processes have shaped Earth's surface and influenced the evolution of life. Ongoing research into the Sun's impact on geological processes is crucial for understanding Earth's history and predicting future changes. Advances in satellite technology, remote sensing, and geophysical techniques provide valuable data on the interactions between solar energy and geological processes. These advancements help scientists better understand the role of solar energy in shaping Earth's landscapes and resources. The Sun's influence extends beyond providing light and warmth. It plays a crucial role in Earth's geological processes. From driving plate tectonics and erosion to influencing soil formation and mineral deposits, solar energy is integral to the dynamic processes that shape our planet. Understanding the Sun's impact on Earth's geology enhances our appreciation of the interconnected nature of Earth's systems and underscores the importance of continued research in this field. As we advance our knowledge of solar energy's role in geological processes, we gain valuable insights into the evolution of our planet and its natural resources. The Sun's radiation has profound effects on human health, both positive and negative. While exposure to sunlight is crucial for the production of vitamin D, which supports bone health and immune function, excessive exposure to ultraviolet (UV) radiation can lead to harmful health effects. Vitamin D is synthesized in the skin through a chemical reaction that is triggered by UVB rays from the sun. This vitamin is essential for maintaining bone health, as it helps the body absorb calcium and phosphorus. Adequate vitamin D levels are associated with a lower risk of osteoporosis, rickets, and other bone-related disorders. Sunlight exposure, combined with dietary sources of vitamin D, plays a key role in maintaining overall health. Excessive UV radiation can cause a range of health problems. Short-term exposure can lead to sunburn, characterized by red, painful skin that can peel or blister. Long-term exposure increases the risk of skin cancer, including melanoma, basal cell carcinoma, and squamous cell carcinoma. UV radiation can also damage the eyes, leading to conditions such as cataracts and macular degeneration. To mitigate these risks, it is essential to use sun protection measures such as sunscreen, protective clothing, and sunglasses. Sunscreens play a crucial role in protecting the skin from harmful UV radiation. They work by absorbing or reflecting UV rays, reducing their penetration into the skin. Broad-spectrum sunscreens that protect against both UVA and UVB rays are recommended for effective protection. Additionally, wearing hats, sunglasses, and protective clothing can further reduce UV exposure. Public health campaigns often emphasize the importance of these protective measures to prevent skin damage and associated health risks. The sun's influence extends beyond biological systems. It also affects technological systems and infrastructure. Solar activity. including solar flares and coronal mass ejections, CMEs, can impact satellite operations, communication systems, and power grids. Solar flares are intense bursts of radiation that can affect communication and navigation systems. CMEs are large expulsions of plasma and magnetic fields from the Sun's outer layer. When these charged particles reach Earth, they can interact with the planet's magnetic field, causing geomagnetic storms. These storms can induce currents in power lines, potentially leading to power outages and damage to electrical infrastructure. Satellites and spacecraft are vulnerable to the effects of solar activity. High-energy particles from solar storms can interfere with electronic components and sensors, affecting the operation of satellites and spacecraft. Space agencies and operators use various shielding techniques and operational strategies to protect these systems and ensure their continued functionality. Solar storms can disrupt radio communications and GPS signals by affecting the ionosphere, a layer of the atmosphere that reflects and refracts radio waves. Disruptions in communication systems can impact everything from aviation safety to emergency services. Understanding and predicting solar activity helps mitigate these effects and maintain reliable communication and navigation systems. Astronauts in space are exposed to higher levels of cosmic radiation compared to those on Earth. Solar flares and CMEs can increase radiation exposure, posing potential health risks such as radiation sickness and long-term cancer risks. Space agencies implement protective measures, including spacecraft shielding and monitoring solar activity, to safeguard astronauts' health during space missions. Solar activity can influence climate patterns, which in turn affect human health and infrastructure. Monitoring solar radiation and its effects on climate helps scientists predict and manage the impacts of climate change. Understanding the interactions between solar activity, climate, and human systems is essential for developing strategies to address and adapt to changing environmental conditions. Ongoing research into the Sun's impact on health and technology continues to advance our understanding and improve protective measures. Innovations in space weather forecasting, radiation shielding, and health monitoring are crucial for mitigating the effects of solar activity. As our reliance on technology and space exploration grows, continued research and technological advancements will be essential for safeguarding both human health and technological systems. The Sun's influence on human health and technological systems is multifaceted, with both beneficial and potentially harmful effects. While sunlight is vital for vitamin D synthesis and overall health, excessive UV exposure poses risks that require protective measures. Additionally, solar activity affects technological systems, including satellites, communication networks, and power grids. Understanding these impacts and advancing protective technologies are essential for maintaining health and ensuring the resilience of our technological infrastructure. As we continue to explore and innovate, we enhance our ability to navigate the challenges and opportunities presented by the Sun's influence.